So our last class of the semester, kind of sad for me. Our last class for the semester will cover atoms. And we're going to talk about the different models or pictures of atoms that have developed over the past centuries, and a modern picture of atoms that we currently think about now, and some of the features of those models of atoms, those pictures of atoms. So specifically, today I want to start by viewing a few different models of atoms that have emerged over the past few hundred years, actually. We'll start with one from Isaac Newton that atoms were kind of tiny, unbreakable spheres. We'll move on to more recent ones. One's called the Thomson's plum pudding model. I'll have to explain what a plum pudding model of an atom is. And the other one was Rutherford's solar system model. And I'll explain what a solar system model of an atom is. We'll then talk about a discovery, a very important discovery, really key discovery about atoms. Now, hot atoms emit light. And it was realized, it was observed that that light is actually discrete frequencies, discrete wavelengths of light, what we call line spectra. This was a huge clue to the nature of atoms, to the models or structure of atoms. And we'll talk about that. And then finally, we'll talk about what's called Bohr's model of the atom. And Bohr's model of the atom is a kind of wave particle model of the atom, incorporating the wave particle nature of matter and light from the past couple of classes. And Bohr's model of the atom actually explains the line spectra, this curious line spectra that's emitted by hot atoms. So that's basically a goal for today's class, to get through these three topics. So let me start with Newton. That's going back a few hundred years. So Newton had the idea that the material world around us is made of tiny atoms, molecules. And his picture of those tiny atoms, molecules was of tiny, hard, indestructible, unbreakable spheres. And his picture of those atoms as tiny, hard, unbreakable spheres had some successes. It explains some things. And I just want to show you one of those successes, one of those things that it explained. If you have a volume of gas, if you have a container of gas, if you have a tank of gas, that gas has some characteristics. That gas has some properties. It has some volume. It has some temperature. It exerts some pressure. Those things, the volume, the pressure, the temperature, are related to one another. Newton's model of atoms as tiny, hard, indestructible spheres, moving in the gas at high speed, at random speeds, in random directions, like in this little picture here. That model of the atoms actually explained the relationships between the volume and the temperature and the pressures of the gas. So that model of the atom as tiny, unbreakable, hard spheres was successful in predicting the relationship between volume, pressure, and temperature in a gas. But that model didn't explain lots of other things, like chemical binding and chemical reactions and other things. And what emerged 100 years ago was two new models of the atom. And these two new models of the atom, I think, is kind of the electrified atom. So what emerged over the 19th century was the understanding of electricity and magnetism. And that was applied to the understanding the models of atoms. And scientists, we'll talk about Thomson, we'll talk about Rutherford, were creating electrified models of atoms. They were creating models of atoms that had electrical components in them, charges in them, that were able actually to explain the binding of atoms and molecules together, the reactions between different atoms and molecules, chemical reactions. So this slide describes what they call Thomson's plum pudding model of atoms. So in his models of atoms, the atom consists of two distinct parts. There's negatively charged electrons in the atom, and they sit in a kind of shroud, a spherical shroud or cloud of positive charge. That's the other part of the atom. And you see this picture of the atom in the center of this slide here. So in blue, look like blueberries, that's the electrons inside the atom. So those are the negative charges inside the atom. And then in red here, that's the positive charge, hypothetical positive charge of the atom. And so if you look at this picture, I mean, maybe nowadays we wouldn't call it a plum pudding model of the atom. Maybe we call it like a blueberry muffin picture of the atom. So the blueberries here are the negative charges. And they're small points or dots inside the atom. And then we've got the cake here. That's the positive charge, medium, or cloud in the atom. And that's what's holding the electrons together. And this model of an atom, this picture of an atom, what was new about it was a electrical atom because it had negatively charged parts and positively charged parts. And with those negatively charged parts, positively charged parts, you could explain why chemical bonding occurred between atoms and molecules, why chemical reactions occurred between atoms and molecules. The chemical bonding, the chemical reactions were electrical in nature. At the same time, about the same time, emerged a second model of an electrified atom. So this is called Rutherford's solar system model. So let me explain that. So in this model, the two components are again, negatively charged electrons. That's one component. But instead of being embedded in a shroud, they're just orbiting a central core, a heavy, dense central core of positive charge. And so that's the second component of the atom. And here's, a little picture of the solar system model of the atom. In the center here in red, that's the positively charged nucleus of the atom. It's where all the mass is, essentially, and the positive charges. And then the electrons are orbiting around the positive charge. They're very light, but they carry charge. And so this was a second sort of electrified model of an atom, incorporating the newly discovered electrons with this time sort of a hypothetical dense core of positive charge. And it too explained the chemical bonding between atoms and molecules through their electrical interactions. It explained the chemical reactions between atoms and molecules through their electrical interactions. So we went back 100 years ago. The real question was, is the atom actually like the plum pudding, or is the atom like the solar system? Which of these two different models of the atom, two different models of an electrified atom containing electrons, known particles, which of those two models is the correct model? So there's a very famous experiment that was conducted to answer this question. And here's a sketch or a depiction of that experiment. So in this experiment, we have over here on the bottom left, there's a radioactive source. And this radioactive source creates or produces a radiation that's called alpha particle radiation. And alpha particle radiation is radiation of heavy, positively charged particles that we call these alpha particles. But just think of them as a radiation, not of light or electromagnetic radiation, but a radiation of heavy, positively charged particles, like little bullets, like little positively charged bullets. So with these lead screens or lead collimators, see the holes, a beam of the positively charged alpha particles, the heavy alpha particles, was produced. And that beam of particles, here it goes, was directed onto a gold foil, a thin gold foil target. And surrounding, so this is gold, this is the target. Surrounding the target were detectors to see the alpha particles, to see the scattered alpha particles that scattered off either the plum pudding atoms inside the gold target or the solar system atoms inside the gold target. And the idea was that the distribution of scattering, the angles of scattering, would be different for a plum pudding model versus a solar system model. And on the next slide, I'll show you how they're different for a plum pudding model versus solar system model. So these detectors around here, when an alpha particle strikes them, they produce a flash of light. They're called scintillators, scintillating screens. And scientists at the time would sit in a dark room with this setup, and they would count the flashes of light in the different scintillators. And in that way, they would measure the scattering of the alpha particles from the gold foil. This slide is meant to indicate the difference that you would expect from directing the heavy, positively charged alpha particles at a plum pudding atom versus a solar system atom. So the top plot sketch, this is plum pudding. This is making me hungry. And the bottom one, this is the solar system. That's making me lonely. And we're picturing alpha particle scattering. So here's an alpha particle heading towards the plum pudding atom. And here's an alpha particle heading towards the solar system atom. And the way I think of this is that the plum pudding has that mass distributed throughout the atom, has its mass distributed throughout the atom. And it's like firing bullets at a soft cushion. Whereas the solar system, that atom has its mass all concentrated at the core. So it's like firing bullets at empty space with a little rock or stone at the center. So what's the difference in the scattering between firing, supposing we went outside right now, we started firing bullets at a cushion and we started firing bullets at a tiny stone. Well, when you fire bullets at the cushion, the bullets just pass through the cushion and they're barely deflected. And so you just see slightly deflected alpha particles in the case of a plum pudding model of the atom. And when you fire bullets at the solar system atom, what do you see there? Well, again, mostly you see bullets that just fly past the center. And again, are barely deflected, but occasionally, right, a bullet will strike that hard, dense nucleus, core of the atom, where all the mass is. And those bullets can ricochet in the opposite direction. And so the key difference between the two models of the atom, the plum pudding and the solar system, is that the plum pudding only features small angle scattering, and the solar system features mostly small angle scattering, but some large angle scattering. And when the experiments were done, what they saw was, well, yeah, there was mostly small angle scattering. That's these alpha particles up here in the top right. But occasionally, look at this guy here, or this guy here. These are large angle scatterings. And so that was the success of the solar system model over the plum pudding model. So at that point, the atom was pictured as a solar system more than a kind of plum pudding. And nowadays, of course, we know that the atom is electrons that orbit around a central, dense, positive core we call the nucleus. Okay. So that was a history of models of atoms. And so now let me move on to the second topic, which is what we call line spectra. And line spectra was a failure for both these models. So both the plum pudding model and the solar system model, despite their successes, failed to explain the line spectra that was seen from hot, when you measured the emission of light from hot elements, from hot materials. So this story started with work, famous work by, if you're a chemist, you know this guy. If you've done chemistry, you know Bunsen burner. Well, the Bunsen burner was developed by Robert Bunsen. And Robert Bunsen developed the Bunsen burner to study the light that's emitted by heated elements. And he observed, measured the different colors of light that was emitted by heating elements. And that way he actually discovered two new elements. He discovered cesium and rubidium. If you heat different elements, here are some examples. As you know, if you burn different gases, for example, or you burn coal or wood or gasoline, for example, you see light, but you see different colors of light. And so I remember doing this when I was in middle school or whatever it was. I basically try and burn everything in sight just to see the different colors of light that was emitted. So if you burn different materials, burn different gases, you see very different patterns of colors. From the sort of over here on the left, it's very much a kind of orangey, reddy, yellowy color flame. Over here on the right, this is butane. It's very much a violet and blue flame. So burning different gases, you get very different colors from those gases. Well, it's one thing to admire the different colors that come from the gases. But with this more sophisticated optics, the more sophisticated understanding of light, the scientists at the time were able to measure very specifically the colors of light, the wavelengths of light, the frequencies of light that were emitted by different atoms, different hot atoms, different burning atoms. And this slide here shows you what we call the line spectra of several different atoms. So in this example, we got the line spectra of hydrogen, we got the line spectra of neon, and we got the line spectra of mercury, 3 different atoms. If you can hear the buzzing right now, there's a big fly in my room, I guess. So there's 3 different line spectra here. So here's hydrogen, here's mercury, and here's neon. And what we're looking at in these 3 different line spectra horizontally is wavelength. And over here on the far left is 400 nanometers. That's the shortest visible wavelength. And over here on the far right is about 700 nanometers. That's the longest visible wavelength. And these are the line spectra of the hydrogen, mercury, and neon. And you can imagine how you might observe these line spectra. For example, you could shine the light on a prism, and a prism would disperse the light into its different colors. And so you could pick out the different colors that way. Or you could use things we've talked about in earlier classes when we talked about optics and we talked about the wave nature of light. You could use diffraction, for example, or interference, for example, to measure the different wavelengths, colors, frequencies of light. But these are the results for hydrogen upstairs, mercury in the middle, and neon at the bottom. And what you see is that, when you burnt the hydrogen or burnt the mercury or burnt the neon and you saw the different colors of light, those different colors of light are made from specific wavelengths, specific frequencies of light that are associated with this or that particular atom, associated with the hydrogen, the neon, or the helium. Well, what was discovered? And I was thinking this must have been fantastic detective story, fantastic detective work. That if you look at the pattern of wavelengths of light or frequencies of light that you get from hydrogen, there was a mathematical pattern to those wavelengths or those frequencies, and you were able to write down equations, formulas for those wavelengths or frequencies. And those formulas for the frequencies and the wavelengths from hydrogen, I've listed them down here. I listed some of them down here. This first equation here is called the Balmer series. And it represents some of the colors or frequencies of light that you get from hydrogen. And then this one here is a second series, Lyman series. It's some of the other colors of light that you get from hydrogen. And I'm going to explain these. Let me just look in chat because I saw a question pop up. Is this saying in Balmer series n cannot be 1, and in Lyman series n cannot be, sorry, in Balmer series n cannot be 1 or 2, and n cannot be 1 in Lyman series? Yes, it is saying that. That's completely correct. They are not arbitrary numbers. And I think you'll see the pattern in a moment when I explain them. So let's look in the Balmer series case. So here's the wavelength in the denominator on the left. So the left-hand side of these equations involves the wavelength. So they're going to predict the wavelength. When we jump over to the right-hand side of the equation, we see this symbol R subscript H. That's called the Rydberg constant, and it's just a constant. It's just a number that has units of inverse meters, and we'll talk about that number in a moment. And then you see a piece here and a piece here that really determines the pattern of light, the pattern of lines in the Balmer series or in the Lyman series. So the Balmer series, its pattern of wavelengths corresponds to 1 over 2 squared, well, that's 1 over 4, minus 1 over n squared, where n is this integer that is greater than 2, greater than the 2 here. And the Lyman series, that corresponds to 1 over 1 squared, well, obviously that's 1, minus 1 over n squared, where n corresponds again to an integer, but now it's greater than the 1 here. And so those are those two series. And if you think about the Lyman series, it would be 1 minus a half squared, the first wavelength. The next one would be 1 minus 1 over 3 squared, or 1/9. The next one would be 1 minus 1 over 4 squared, or 1 over 16. And if you thought about the Balmer series, it would be 1 over 2 squared, so a quarter minus 1 over 3 squared, so minus 1/9. A quarter minus 1 over 16, 1 over 4 squared. And so those are the patterns. These equations are describing the patterns. Upstairs here, I've actually pictured the Balmer series. So this is the hydrogen Balmer series. This red line here, this guy over here. So this is a red line. It's about 660 nanometers. And it's given by n equals 3. So n equals 3. And this second number 2 is this number 2 here. And that gives, with the Rydberg constant, 660 nanometers. The second line in the Balmer series, that's when n is 4. And that's this line here. And that gives a line that's, I think it's about 486 nanometers, something like that. Again, you get it from this equation. And then the third line in the Balmer series, that's over here. It's when n equals 5. When n equals 5, you've got a 5 here, you've got your 2 here, this line here. This one's in the blue. And then n equals 6 actually is in the violet. It's this line here. And it continues on beyond that. So here's the Balmer red, azure, I think is the color they call it, blue and violet. That's the 3 to 2, the 4 to 2, the 5 to 2, the 6 to 2 from upstairs here. But then beyond that, there's a 9 to 2, 10 to 2, 11 to 2. These are all in the ultraviolet. And they're all sitting up here. These are wavelengths you couldn't see with your eyes, but you could detect with instruments. Now, the importance of this was it was a massive, massive clue to the nature of atoms, the structure of atoms, the true picture of atoms. You had to explain why you get these characteristic Balmer series, Lyman series patterns from emitted by hydrogen. Let me just make a remark about that constant that's in those equations. So the stuff in parentheses for the Balmer series equation or the Lyman series equation, those are just numbers. Those are like 1/2 squared minus 1/3 squared, or they're like 1 minus 1/2 squared. Those numbers are multiplied by a constant. We call it RH, it's the Rydberg constant, and that carries units because the left-hand side has units of inverse length. It's 1 over a wavelength. And here's the Rydberg constant. It's about 1.08 times 10 to the 7 inverse meters. And that sets the scale of the wavelengths, and it sets the units of the wavelengths. So the Rydberg constant is important. If you were to change the Rydberg constant, okay, so supposing, I mean, of course I can't, but supposing I could turn a dial and change the Rydberg constant. If I turn that dial and change the Rydberg constant, I don't change the pattern of the colors of light, the arrangement of the colors of light. I just change the overall scale of it. I stretch it out or I compress it if I make the Rydberg constant bigger or smaller. So I'm just changing the overall scale. Key thing is these equations, which were found empirically, they were discovered empirically. They just were found to match the line spectra of hydrogen. The key thing is they were a massive, massive, massive clue to the true nature of atoms. And they were also completely unexplainable with a solar system or a plum pudding model of an atom. And so those are important points. Okay, I wanted to, before we explain them, just give you one example of calculating the wavelengths of light with Balmer, Lyman, and what we're going to work with is the Paschen series. So the Lyman series, in parentheses, the first term was 1 over 1 squared. In Balmer series, the first term was 1 over 2 squared. There's other series too. The next one is Paschen series, and the first term is 1 over 3 squared. So I partly wanted to introduce that set of line spectra, what we call the Paschen series for the hydrogen atom. These wavelengths are much longer. These frequencies are much shorter than the Balmer series, the Lyman series, and these are actually in the infrared. And for these, this is the equation. So this is not a 1 over 1 squared or 1 over 2 squared, or it's a 1 over 3 squared minus 1 over n squared. And now the n is again integers larger than the 3. So the n is a 4 or a 5 or a 6. That's the pattern. And so we can use this equation to calculate the first 3 lines of the Paschen series. And that's what I've done downstairs here. So n equals 4. I'm going to calculate the wavelength. I'll calculate the inverse of the wavelength by multiplying the Rydberg constant, here's its value, by this difference of 2 fractions, 1 over a third squared minus 1 over 4 squared. So 1 over 9 minus 1 over 16. And that gives us the inverse wavelength. And if you calculate the inverse of that to get the wavelength, it's 1875 nanometers. So it's a lot longer than visible light. If you do the n equals 5 case, again, to find the inverse wavelength, you just take this empirical equation for the Paschen series, and we're going to multiply the Rydberg constant, RH, by this difference of two fractions, 1/3 squared minus 1/5 squared. So it's 1/9 minus 1/25. And if you calculate that, you get this little number here. The inverse of that is a wavelength is 1281 nanometers. And so on and so on. Here I won't go through it, but here it's done for n equals 6, the next term in the Paschen series. Then it would be an n equals 7, and it would be an n equals 8. And you could keep on going and going. So at that point, there was kind of a race in what we would call quantum physics, or physics of atoms and molecules. And the scientific race was to explain, understand these line series. And it was Bohr's wave-particle model of the atom that first explained these line series. And so now we're going to turn to this kind of third topic. Oops. We're going to turn to looking at Bohr's model of the atom. So what is this model of the atom? What is, in particular, this wave-particle model of the atom? So the solar system model of the atom was sort of particles. And the Plum pudding model was sort of particles. Both of them had electrons as particles inside the atom. And then the solar system model had this small, heavy core, another particle in the atom. The Plum pudding model had this larger kind of cloud or lump, another type of particle in the atom. What Bohr's model was no longer just a picture of an atom as an assembly of particles. It was a wave-particle picture of atoms. Okay, so I wanted to remind you of this slide. So this is an old slide. We've met this slide before, because it kind of lists the two ingredients that Bohr built his atomic model from. He built his atomic model from a combination of the, sort of quantum description of matter and the quantum description of light. And if you remember that, classically, we would think of particles as localized, discrete objects. But in quantum physics, we think of them as having a kind of fuzziness, a diffuseness, and then exhibiting interference and diffraction, and having an associated frequency and wavelength. So this is the relationship between the frequency and the energy of a particle, the wavelength and the momentum of a particle in quantum physics. And so this is an important ingredient in Bohr's model of atoms. And then classically, we used to think of electromagnetic radiation as a wave. But in the quantum description of electromagnetic radiation, we think of it as being emitted and absorbed and propagating as kind of little particles, little corpuscles of light. So it has particle-like properties. And so that is the quantum description of light. And for light, electromagnetic radiation, we think of those packets as carrying an energy and momentum, and that energy and momentum being related to the frequency and the wavelength of the light. And so over here on the right is the quantum description of light, And over here on the left is the quantum description of matter. It's kind of this unified description of matter and light. They're both wave particle objects. Matter now has a fuzziness to it. Light has a granularity to it. And Bohr put together these models of atom and light, these quantum models of atom and light, to build a model of the atom that explained the line spectra of the light. Okay, well, I want to show you a picture of Bohr, I guess. He won the Nobel Prize for this work. So it's very famous work to come up with this explanation of the line spectra of atoms, to come up with this new, unique model of atoms. So this slide and the next slide show you the particle-like properties of Bohr's atom. That's this slide. And the next one is the wave-like properties of Bohr's atom. And then the third slide in this series will be the consequence of combining the particle-like and the wave-like properties of atoms. So that's how we're going to go over the next 3 slides. So let's start with the particle-like properties of the atom. And so here's Bohr's atom from a particle perspective. And in the particle perspective, we've got a nucleus, the center here, where the mass is. And then our electron is orbiting the nucleus on this circular orbit in blue here. And it's orbiting due to the electrical attraction between the positively charged nucleus and the negatively charged electron. That creates an electrical force that provides a centripetal force that causes the circular motion. And in that particle-like picture of an atom, where the electrons are circling around the nucleus, just like in a picture of the solar system where the Earth is circling around the sun, the understanding here that the electrical interaction rather than gravitational interaction provides the centripetal force for the circular motion, that understanding relates the speed that the electron is traveling around the atom, so this guy here, its speed, to the radius of the orbits of the atom. i.e., for a given radius of orbit, there's a particular speed the electron will orbit at, or for a given speed of the electron orbit, it must be orbiting at a certain radius. So that's dictated by the fact that that electrical interaction is providing a centripetal force. So that's the particle-like perspective. Let's turn to the wave-like perspective. So here's the wave-like picture of Bohr's atom. So in his wave-like picture of the atom, this wave here, this is the matter wave of the electron orbiting the nucleus at the center. And you see that wave cresting and troughing as we walk around the orbit. And Bohr's idea, Bohr's sort of radical new idea, was that these matter waves had to fit exactly in the orbit. You had to have a whole number of wavelengths around one complete orbit. And so I think you see this in this case. Look, here's an example. This is one wavelength. This is a second wavelength. And then around here, this is the third wavelength. And so we've got 3 whole wavelengths fitting in the this particular orbit for this particular example of a Bohr matter wave atom. And so the idea is you can't have any wavelength for a certain size Bohr orbit. You can only have wavelengths that exactly fit in the Bohr orbit. If you had a different wavelength, what would happen is it would destroy itself. It would undergo destructive interference, and that matter wave would disappear. So the only stable matter waves are the ones that exactly fit with whole numbers of wavelengths around the Bohr orbit. And so that's what's indicated here. That instead of being able to have any radius orbit or corresponding to any speed for the orbit, because the matter waves have to fit in the orbit, that means that there are only certain radius orbits and certain speed orbits that are allowed in the wave particle Bohr atom. So no longer can you have any allowed radius and any speed. You can only have certain radii, certain speeds, and they're labeled with a subscript n here, where n's are integers. So the n equals 1 would be the first matter wave that fits in the kind of atomic box. The n equals 2 would be the second matter wave that fits in the atomic box. This would be n equals 3. It's the third matter wave with 3 full wavelengths that fit in the atomic box. And so for each of those, there's an R1 and a V1 for that first matter wave that fit in the box, and R2, V2 for the second matter wave that fit in the box, and R3, V3 for this matter wave that fits in the box. So that's the idea. Well, so if you put that wave particle, that wave picture of the Bohr atom together with the particle picture for the Bohr atom, you get a number of important results. And so by just putting together these two pictures, so remember this is on the left here, this was the particle-like view of the atom, and over here on the right, this is the wave view of the atom. And putting them together, we've been able to conclude that only certain orbits are stable in atoms. Only certain orbits that have certain radii, certain wavelengths, and we label them with an integer n, 1, 2, 3, corresponding to the number of wavelengths that fit in the box. Now, importantly, the radius of the orbit, that's going to govern the electrical potential energy of that arrangement. So the closer or further away the electron is to the nucleus, the positive charge to the negative charge, that's determining the electrical potential energy. So Rn governs the electrical energy. Vn, the speed for that orbit, well, that's going to govern the kinetic energy. So that will determine the kinetic energy. And then finally, the sum of the potential energy determined by Rn and the kinetic energy determined by Vn, that's going to govern the total energy associated with that particular orbit. So this is important, that these allowed orbits have corresponding allowed energies. And so there are only going to be certain allowed energies, and we're going to call those En. Then finally, let me make this comment, that also, if you can only have certain radii and certain speeds, Rn's and Vn's, then that means that you can also only have certain angular momenta. If you remember from 211, the equation for angular momentum in terms of the speed and the radius of the rotating object is the mass of the object times the speed times the radius of the orbit. And so if Vn and Rn, only certain values are allowed, like V1, R1, V2, R2, then only certain values of orbital angular momentum are allowed. And so this was a huge consequence for his model of the atom. if you went to the solar system model of the atom, or you went to the Plum pudding model of the atom, you could have any energies you like for the atom, depending on the speeds and of the electrons in the atom, the distance they are from the positive charge in the atom. You could have any potential energies you like. You could have any kinetic energies you like for the electrons in the atom. There was no limits. But in the wave particle picture of the atom, there are limits. There are only certain orbits. There are only certain values of kinetic energy, potential energy, and total energy that are allowed. And so that was the breakthrough. That was a massive breakthrough. On this slide, I'm just going to give you a couple of equations, really. Oops, sorry. Based on those arguments about only certain radii being allowed, only certain speeds being allowed, only certain kinetic potential and tonal energies being allowed, you can write down equations for the energies of the orbits in the Bohr atom. And here's that equation. And it's not very complicated. The energy of the nth orbit, so this could be the first orbit, the second orbit, the third orbit, the fourth orbit, so on, is a constant, minus 13.6 electron volts, divided by the square of n. So if it was the first orbit, then it would be minus 13.6 electron volts. That's its energy. If it was the second orbit, it would be minus 13.6 electron volts divided by 2 squared, or 4. So those are the energies of the orbits. In addition, there's allowed energies of angular momentum. So remember, the angular momentum was also dictated by what values of r and v are allowed. And here's the equation for the angular momentum. It's the values of angular momentum, so L subscript n, so the L1, L2, L3, and so forth. Those angular momenta had the values of Planck's constant over 2 pi times n. So remember, Planck's constant is associated with the scale of the granularity of matter, sorry, of photons and the fuzziness of matter. And it sets the scale of the angular momenta of the electrons in an atom. And these n's, they describe the particular orbit. N equals 1, n equals 2, n equals 3, and so on and so forth. We actually call the lowest value of n equals 1, we call that the ground state. It's the most bound atom state. We call n equals 2, we call that the first excited state. It's the next most bound state. And then so on and so forth, right? N equals 3 would be the second excited state. It's the next lowest state. And there's an interesting point here, a relationship here about that energy. So firstly, that energy is negative because you would have to add energy to the atom to remove the electron. Secondly, that energy, as I say, is the sum of the kinetic energy and the potential energy. But the kinetic energies and potential energies, the total energy, are related in an interesting way. The kinetic energy is twice the potential energy. And it's the opposite sign to the potential energy. Actually, I think I have this the wrong way around. So I think this is a mistake. No, it is not a mistake. Gosh, I'm always thinking I'm making a mistake, and I'm not making a mistake there. This is not a mistake. The potential energy here is twice the kinetic energy. So half the potential energy is equal to the kinetic energy. And it's also the opposite sign. It's negative. And so that's an interesting relationship between the kinetic energy, potential energy, and the total energy in the Bohr atom. And it's actually also true for the planets in the solar system. There's the same relationship between their gravitational potential energy, their kinetic energy, and their total energy. Okay, I got a quiz here. Okay, let's just review the answer to the quiz. So the energy of a particular state in a Bohr atom, so we call that energy En. That energy is a constant. It's a constant with the units of energy, electron volts, is the normal unit of energy for atoms. It's minus 13.6 electron volts divided by n squared. So that means the bigger the n for the particular orbit, so the more wavelengths that fit in the box, then the smaller the binding energy. The easier it would be to remove that electron from the atom. If we want to compare the ground state and the first excited state, well, the ground state is n equals 1. So its binding energy is minus 13.6 electron volts. The first excited state is n equals 2. Its binding energy is a quarter of minus 13.6 electron volts. So the answer here is that the binding energy of the ground state is 4 times the binding energy of the excited state. So I hope that makes sense. Here's a picture. Here's a sketch that emerges from Bohr's wave particle model of the atom. And it's called an energy level diagram of a atom, of the hydrogen atom. And it shows the energy levels of the hydrogen atom together with the line spectra that are emitted from the hydrogen atom. So there's a lot of information, a lot of interesting information on this plot. So firstly, the vertical axis is energy. And 0 binding energy is upstairs here. And increasing binding energy is downstairs here. And the ground state is this horizontal line here. So this has a value of n that's 1, that's the ground state, and it has a binding energy that's minus 13.6 electron volts. The first excited state, that's this, okay, here was the ground state. Here's the first excited state, n equals 2. And its binding energy is 13.6 over 2 squared, over 4, and that's 3.401 electron volts. And that's the pattern that continues. So here's the second excited state, that's n equals 2, and its binding energy, that's 13.6 divided by 3 squared, divided by 9, that's 1.5 electron volts. And then so on for the third excited state, its binding energy is 0.85 electron volts, and so on and so forth. So this is an energy level diagram. You're seeing the allowed orbits and the energies of the allowed orbits. They're related to the radii and the speed of the allowed orbits in the hydrogen atom. So that's one important feature of this diagram. But the other feature of this diagram is that you can picture the light that's either emitted or absorbed by hydrogen atoms. So the Lyman series, remember that series of lines? That's these lines here, these vertical lines. So the light on this diagram is vertical lines. And this shortest line, that's actually the longest wavelength, the lowest frequency Lyman series line. And that's from the first excited state down to the ground state. So it's a transition from n equals 2 to n equals 1. And that's the first line in the Lyman series. And then the second line, that's a higher frequency, a longer wavelength. No, a shorter wavelength, sorry. And that's from n equals 3 to n equals 1. And so on and so forth. So that's the pattern of the Lyman series lines that were described by that Lyman series equation, described by the equation that the inverse of the wavelengths is the Rydberg constant times, in parentheses, 1 minus 1 over n squared. Here's the Balmer series, these lines here. These are the lines that the final state is the n equals 2 level, not the ground state, it's the first excited state. And these are the lines, if you remember, they're in the visible part of the spectrum. So the longest wavelength, the highest frequency line is this line here, the lowest frequency line, this red colored light here. And then so on and so forth. We got the azure, we got the blue, we got the violet. And then here's the Passion series of lines. These are in the infrared. These are not visible. These are the ones that we calculated as an example of using the Passion series equation. And so this is a very important, very handy plot in that it shows the energy levels and it shows the line series. So on this slide, I'm just showing the same figure. Oops. Upstairs here, same energy level diagram, same line spectra diagram. But I'm just pointing out the frequencies of the light that are predicted by this model. They correspond to the energy differences between the different states divided by Planck's constant. That's the relationship between energy and frequency for light. And the wavelengths of the light, where they're related to the frequency and the speed of light, and they're given by this equation based on the energy level diagram. So this diagram leads to these two equations for the frequency and the wavelength of light, based on the wave particle model. And importantly, look at this little bit here. This little bit here, it's actually predicting the Rydberg constant. So one of the successes of the model was that no longer is the Rydberg constant just a constant that's measured. Now the Rydberg constant is actually a number that is predicted by the model. And so that was a big verification of the model, that the Rydberg constant relating the n's to the wavelength or the n's to the frequency was now a predicted number. Okay, want to show you in the last few minutes just a couple of examples of working with these equations for the hydrogen atom. So in this slide, I'm just going to compare the total energy, potential energy, and kinetic energy of the ground state. And we're just going to do this quickly with some of the equations that we've just met on the last couple of slides. So the energy of the nth state in an atom, hydrogen atom, is minus 13.6 electron volts over n squared. So the ground state energy, n equals 1, that's going to be minus 13.6 electron volts over 1 squared. So it is just minus 13.6 electron volts. That's the binding energy of the ground state. What's the potential energy? Well, I said that the potential energies, kinetic energies, and total energy, binding energy, I have an interesting relation to. The potential energy is actually twice the size of the binding energy. And so for any orbit, any allowed orbit, the corresponding electrical potential energy of that orbit is twice the total binding energy of that orbit. So for the nth orbit, the first orbit, n equals 1 orbit, here we're talking about n equals 1, the potential energy is twice the binding energy of that first orbit. So it's twice minus 13.6 electron volts. It's 27.2 electron volts. So that's the potential energy of this ground state. And then finally, if you want the kinetic energy is actually the same size, but the opposite sign as the total binding energy. And so that's true for any orbit. And for n equals 1, the kinetic energy of that first orbit is the negative of the total energy of that orbit. So it's minus 13.6 electron volts. Of course, kinetic energy is positive. It's positive 13.6 electron volts. And so that's the kinetic energy of that ground state. And you can always check your numbers, right? The total energy is the sum of the kinetic and the potential energies. The total energy is 13.6 electron volts plus minus 27.2 electron volts. That is minus 13.6 electron volts. So that's an example of energies in the atom. And then finally, here's an example of line spectra from that model of the atom. It's about the line spectra of the hydrogen atom that comes out of the wave particle model of the hydrogen atom. We're told that hydrogen emits radiation at 656 nanometers. That's the red colored light from hydrogen. And we're asked to figure out what transition that is. So faced with that question, being told that there's this wavelength of light, what is the transition that corresponds to? My first step was to say, well, that transition, that wavelength of light corresponds to a certain energy of photons, a certain energy difference between energy levels. And so I calculated the energy of the photon. I calculated the energy of the transition. So the energy of the photon is Planck's constant times the frequency of the photon, and the frequency is related to the wavelength of the photon. I know all those numbers, Planck's constant, the speed of light, and the wavelength. I can find the energy corresponding to 656 nanometers. It's about 1.9 electron volts. And then I can consult my energy level diagram, really. What difference between levels corresponds to, what levels corresponds to a difference of 1.89 electron volts? So I've got to go searching through this energy level diagram. Well, as a reminder, the ground state is 1.6 electron volts. The first excited state is minus 3.4 electron volts. The third excited state is 1.51 electron volts. The fourth one is 0.85 electron volts. What you can do is look for a difference of 1.89 electron volts. And maybe you can see it here. The difference between the first excited state and the second excited state at minus 3.4 and minus 1.5 electron volts is 1.9 electron volts. And so that transition upstairs here, this one here in the Balmer series, is that particular 656 nanometer wavelength light. Anyway, let me finish there. Today's class, we covered a few things. Let me just remind you. We reviewed some old models of the atom, from Newton's oldest model of the atom as hard, unbreakable spheres, to 100-year-old models of the atom involving electrical components and explaining chemical reactions, chemical bonding, to more up-to-date quantum physics model of the atom that could explain the wave particle nature of the atom and the discrete line spectra that you get from atoms. So this is the world of atoms and molecules that we know today. I'm going to finish there. Let me first thank you for taking the class. It's really been a great experience. You've been great students in this class. You kept up with the work so well. I was really impressed by that.